Welcome back. What a wonderful video. I would like to now introduce Taka Kubota. Taka is a third-year PhD student at the University of Delaware's Department of Materials Science and Engineering, and he's conducting research at the Center for Composites Materials. Taka, welcome to Imagine Aviation.
Thank you for having me.
So there's some questions already we want to dig into here on the work that you highlighted in that video, and a wonderful video it was. But how is TuFF stretching and the flexibility characteristics being used for novel aircraft designs?
So what's really nice about TuFF that we can't do in conventional composites is when we go and stamp form, we're able to actually be able to stretch the composite as the forming is happening. That can't happen in conventional composites because of the continuous fiber nature. And what's really nice is that the stretching that can happen without damaging the fibers can actually create these complicated features that are not conventionally possible using composites or in some cases with metals.
Really interesting. So this new paradigm shift that you're proposing for these highly aligned short fiber composites, are you suggesting they can be stamped like sheet metal, almost like at a high rate? So is this suggesting that you're almost transitioning from the way we manufacture today to almost the speed and quality the auto industry does?
That's exactly right. That's what's so exciting about TuFF is that previously composites were hand laid up. It was very much a skill dependent process that took hours and hours. But TuFF actually can use these presses that are currently being used in automotive industries for higher volume parts. And all we're suggesting is, swap out the sheets of metal and put TuFF in there and use that press without buying anything new and just start stamping parts out.
Oh, that's really exciting to imagine a world where that can happen. So there is a question that's related in the chat is, what is the mechanical strength in comparison with classic woven carbon materials?
So what's really cool is that when we optimize the interface between the fiber and the matrix, what we can do is actually get near continuous fiber composite properties, even though we're actually using these short fibers. And how that works is by basically optimizing that interaction between the fibers. You can then transfer the load to the neighbor fiber and so on and so forth. So you're actually, even though they're not connected, you get these near connected or continuous fiber properties.
Oh, wow. So how do you attach multiple TuFF panels? I mean, can you use traditional fasteners, or does the use of those fasteners, then you would lose some of your weight savings?
So there's various different ways we can go about attaching these pieces. What's really cool is one, we actually have the flexibility of creating these large complicated pieces in one go. So you have the opportunity to avoid using joints. You could definitely use conventional joints, but you can also use adhesives that are actually conventionally used. Depending on the matrix, if it's a thermoplastic, we can actually also weld them together as if you were welding metal together.
Right. Oh, that is very interesting. So we've covered a few of these wonderful things. Your video explains some of the wonderful positive aspects, but it wouldn't be true to ourselves if we didn't ask you, what are some of the biggest barriers with the TuFF technology, and how are you attempting to mitigate those barriers?
So right now, throughput, it is a very new process. We're still working on because composites tend to be a complicated system where you have your fiber and then you have your matrix, and they have to mate together very well. We're trying to really look into how do the interface properties, how do the micromechanics, how do the microstructure all affect the overall performance. And it's still new, and then also the forming. We're learning, how much can we form without losing properties? How thin can we go? And some of these conventional demerits may actually turn out to be favorable for us because of how we can control the thinning.
It's good to know that some of those things that identify themselves as barriers may not be as tough. You might have nice leads on addressing some of them. One of the ones that will pop up down the line and thinking far out is what type of certification does this material and process have to go through compared to conventional materials used for airworthiness?
Right, right. So the FAA certification is a tough question because we are using aerospace grade fibers. We're using aerospace grade matrices, and in combination. So the question becomes, how does the actual fact that they're discontinuous affect the certification process? Yeah, that is something that will need to be addressed.
Absolutely. But it sounds like it's worth it if to investigate some of those tougher components. If you do talk about that, almost like the first question that came to mind was about the speed of production. How does that? Have you done any calculations or translating or worked with any of your industrial partners of how much costs or time savings can this benefit aircraft manufacturers?
Right. So as I said before, conventional carbon epoxy system may require, say, I don't know, 6 hours in an autoclave, and frequently parts are delayed because you can only put so many parts in the autoclave at a time. But switching over to, say, a thermoplastic system, where you can just stamp, and you may have a few minutes of heating up the preform, and then stamping it will only take a few minutes. You're looking at a significant fraction of time reduction and energy reduction. So from that perspective, I think there's a lot of positive aspects, but I have not done the actual math. Right. Well, personally, I have not. I'm sure our industrial partners are looking into all of this and putting time to money and hopefully getting very excited, as much as excited as I am.
Absolutely. Yeah. And that brings up a great point too. And that's some of the benefits we've already heard for the university leadership initiatives and the efforts you're working on. How does ULI and activities such as TuFF and the work you're doing, how does that further develop and prepare students for what to expect from the workforce and industry needs of the future?
Yeah. So I think one of the great things about these opportunities and being able to work with industrial partners is, I basically spent all my, life so far, school, and I know what school is like. But to get a sneak peek into what my next stage in life will be, say in industry or in other government labs, is a great opportunity that I don't really get without. Yeah, so it's a great opportunity to kind of take a peek at what my life will be looking like in the next few years.
How have you found some of those industrial partners? How have they welcomed the students into this, yourself and some of your peer students? Have you found it really refreshing and enlightening that they do welcome in the work of yourself and your peers?
Yeah, definitely. They've been very welcoming, and it's really great to engage and see. Our professors have very different priorities than, say, industry does, and kind of getting that exposure is wonderful.
No, that is great, and it's really, I think that's the goal, one of the goals of this program. So it's excellent to see that. So we've heard a lot of a brief statement of this technology and how we could use it for aviation and the above. But are there any other applications that can use this technology besides aviation? Do you have any examples of those?
So what's really cool about TuFF is that we actually can take the end-of-life parts or waste in production, actually reincorporate it and upcycle that material to make basically anything, whether it be, going from, it would have been just trash to an actual product like parts in a car or any other kind of light application that will really benefit in lightweighting. So, going from, something that would have just been tossed away into landfill can actually become products with this technology.
Oh, that's great. And we are going to obviously talk a little later about have a panel that you're going to be a part of on sustainability. But can you tell us a little bit more about the sustainability characteristics of TuFF? Is it green by nature? Or?
Yeah, so the idea is that, we can take all of the energy that we've already incorporated, embodied into, say, carbon fiber or making these prepregs. And if it's end of life or recycling, what's really nice is that we can actually then take the resin out and realign it. And why that's sustainable, is that we're actually we're giving, just like recycling of anything else, we're giving it another opportunity and balancing out and reducing the impact of the embodied energy that went into it, and giving it a new life, and hopefully the benefits of composites again.
Oh, that is great. We're out of time for the Q&A. Taka, Kubota from University of Delaware. Boy, it's such a great project, and you can see the passion that you embody with the work and your answers, and it's lovely and very exciting. And we can't wait to hear more about this in the future and talk to you real soon in the sustainability project. So, Taka, thank you very much.
Thank you very much for having me.